All right, welcome everyone. So today we're hosting Thiago Guerreiro from Pontifical University of Rio de Janeiro. So he's an experimental physicist in the field of levitated optomechanics, but also has some really interesting works on testing for signatures of non-classical states of gravitational waves and the quantum nature of gravity. So today we'll be hearing about his works in that direction. So when you're ready, Thiago.
Okay, so thank you very much, German. So first of all, I'd like to the organizers for inviting me here. It's a real pleasure. So I want to tell you some ideas on this interface between quantum mechanics and gravity. And I like to start with this Gedanken experiment by Richard Feynman. I think he presented this in a conference, but you can read about it in his book, Feynman Lectures on Gravitation. So here, Feynman wanted to argue that we need to have a quantum description for gravity. And the argument is very simple. So let's say, suppose you are able to place a massive object in a superposition of two different locations. Okay. Since this object is massive, it's gravitationally important. The field will be strong enough so that you can measure, and then the field itself will be in a superposition. So say if you attribute an amplitude for the object being in this upper part of the screen or the lower part of the screen, then you will also have to have amplitudes associated to different space-time configurations. So this is the standard thing in quantum mechanics, right? And Feynman uses this as an argument for the quantization of the gravitational field. But then you have folks like Roger Penrose who are approaching this problem from a more general relativistic perspective. And Penrose says, okay, wait a minute, there's a problem here. And the problem goes something along these lines. So if you want to speak about this mass in a superposition of different locations, you need to speak about the space-time metric, okay? But what does it mean to talk about the space-time metric in this case? In this situation, you would have in one branch of the wave function a space-time configuration or a manifold with a certain metric. And in the other branch, you would have another configuration with another metric. And in general relativity, there is no observer-independent or gauge-invariant way of comparing these two space-time manifolds. You need to, have a point identification between these manifolds, and just point identifications in general relativity are arbitrary because they're equivalent to coordinate transformations. So, of course, we know that Penrose's way on this is going towards saying that gravity is essentially classical and that it enforces classicality in the world. You may or may not agree with that. That's a matter of personal taste until experiments will settle the debate. But this points out, in my view, that there's something really odd going on here. And it's very important, this question of what happens if you try to superpose different space-time configurations. Then there is the further point of view that it doesn't matter. Okay? Quantum gravity doesn't matter because any phenomenon that you could possibly have, which involves quantum mechanics and gravity in the same picture, they're just so tiny that general relativity is such a good approximation that you simply don't care. Okay? And you can understand that by looking at the coupling constant of elementary particles like an electron or even an atom to the gravitational field. This is regulated by this dimensionless quantity here, which is basically the energy of the electron divided by the Planck energy. And this is ridiculously tiny number, 10 to the minus 23, it turns out. So this immediately tells you that the scattering cross-section of electrons or atoms to single gravitons or quanta of the gravitational field is completely negligible. So this, is the basis of this viewpoint that quantum gravity simply doesn't matter, and we can go along with general relativity. But then you have people like Bill Unruh in this very nice article here, who argue that this is not the case. You cannot neglect quantum gravitational effects, because in order to see them, you simply need to use gravitationally important objects. Okay, using an electron is a bad idea, but it turns out that there are objects in the universe which couple very strongly to matter, and these are large aggregates of matter. So, for instance, Bill uses this example, which I like very much, is theory at its best, which you take a neutron star, okay, and you cool it down to its fundamental mode, So neutron stars can vibrate, they have internal vibrational modes like any lump of matter. And now if you excite the first excited mode, this can decay and it will emit a single graviton. And you can make this single graviton pass through, say, a black hole. And if the black hole has a radius of curvature, which is comparable to the wavelength of the gravitational wave, then this will create an interference pattern, just like a double slit or like a single slit diffraction experiment with a perfect absorber. So there you go. You created a quantum superposition of quantized gravitational wave in different locations of space-time, and this cannot be explained by classical mechanics. Of course, you may argue that this is an impractical experiment, and it is, of course, but this tells you that in principle, there are objects in the universe for which the quantum nature of gravity should matter. And if there are such objects, even in principle, then maybe we should worry about the quantization of gravity. Okay, you can say, okay, how do you detect this gravitational wave? Well, you simply take another neutron star, now cooled to the ground state, and you hope that the graviton scatters this neutron star, and it will have a very large coupling constant. In this case, it's 10 to the 38, if you do the math. And then you can witness, these continuous jumps of this neutron star internal vibrational modes, which are due to the quantum nature of the gravitational field. I should point out that Germain Tobar and his collaborators recently put out a very nice paper at Nature Communication on detecting single gravitons, which uses just these ideas here, but not using neutron stars, of course, but using bars and quantum metrology. So this may not be such a hard, far-fetched experiment in the end. But I think this gives us a clue. Okay, by the way, during my talk, I have many, many ideas, so I'll just, place some clues now and then, and these clues, we should keep them at the back of our minds. I think they're important, and they will come back to us in the future. So Bill Unruh's clue, I think, is that if you want to see the quantum nature of gravity, if you want to certify the quantum nature of gravity, then we need gravitationally important objects. In other words, you need the high coupling of gravitons or of gravity to matter, okay, or to the object, to the detector that you are using to probe these effects. There's another clue hidden here in the black hole, which is that in order to create non-classical states, you also need nonlinearity. Okay, and this is exactly analogous to the double slit. If you look at the usual double slit experiment in quantum mechanics, and this is something that the people in the levitated optomechanics community have been discussing quite fiercely, that in order to show interference patterns, you need nonlinearities, you need nonlinear interactions. The double slit is nonlinear interaction or nonlinearities given by the slit here. So this actually is what prepares the quantum states in a non-classical state where you have interference patterns and so on. And then you need the detector. Okay, so that's another clue. We need nonlinearities. Okay, so during this talk, I'm going to take the standard viewpoint. Well, what I like to think of as the standard viewpoint is that we do have a quantum theory of gravity. It's a low energy theory, okay, but we don't care. It's a good enough model, okay, as long as you don't go to Planck energies or any crazy high energies, that should be fine. And this model has predictions. So it predicts, for example, loop effects. Okay, this famous prediction of Blankawi on the modification of the gravitational force. And it predicts cat states. You can have superposition states of on-shell gravitational waves, for example, which are non-classical and that cannot be explained by general relativity. By the way, these states are allowed by the theory, but that doesn't mean that they actually exist in nature. So we have to exert caution. We have to, be very, very careful. And this will lead us to two parts in this talk. So in the first part, we are going to assume that these states exist, and then we'll derive some consequences of their existence, and then we will move on and ask ourselves, okay, but do they really exist? Okay, but that's for the future. And there's another aspect of this thing, which is that this low energy description of quantum gravity, well, it is quantum, so the gravitational force in this theory is mediated by virtual gravitons. And you have things like this Bose-Marletto-Vedral argument, which says that if you have two delocalized masses, two masses in superposition of different locations, and if you guarantee that each one of them interacts with only via the gravitational field, then if you witness the entanglement of these masses, this implies by a quantum information argument that the gravitational field needs to be quantized. Okay. So this splits the field into what I think are two major directions. One is a tabletop direction where you want to create massive quantum superpositions in the laboratory and you want to witness things like entanglement, gravitationally induced entanglement. And the other is an observational program, which is basically trying to measure quantum gravitational wave states or gravitational states which are produced naturally in the universe. Okay, so it's nothing that you can control in the laboratory, but they might exist out there. So today I'm going to focus on the observational program, but in my lab, we're also working towards this tabletop program. Okay. I think the tabletop program will eventually work. It's a very daunting experimental challenge, and there's a lot of things that need to be improved, and there are a lot of ideas that need to be put forward yet. But it's a very interesting thing, but I really believe that this observational program is a nice thing to work on. So, okay, let's go to part one. Okay, let's pretend that non-trivial quantum states of gravitational waves exist in nature. Okay, why do we think, or why could we think that these states exist in nature? Well, for one thing, we have optics. We have a lot of experience with quantum optics. And there are many, many examples of non-classical states in quantum optics. Okay, here I've separated two of my current favorite examples. They change all the time. I have moving tastes. So at the moment, these are my favorite. So there is this impressive work by the group of Gerhard Leukes, where they show polarization entangled light pulses with 10 to the 5 photons. Okay, and once again here, you have these nonlinear crystals. So remember the nonlinearity clue I was telling you about. So these are parametric down conversion crystals. It's a 3-wave mixing nonlinear process. And you can use them to create these states where you have two modes and you have many, many photons in each of the modes, but the polarization in these photons are always correlated. So if you measure the polarization in one arm in a certain direction, all the photons in the other mode will have the same direction. Okay. And then you can come up with some field correlators and some functions of field correlators which can only achieve certain values if you have entanglement. So you need to certify this entanglement. And people have done that many, many times. This is just one example. And it shows that you can have macroscopic or mesoscopic quantum states of the light field in non-classical states. Another example is by these guys from São Paulo in the group of Marcelo Martinelli and Paulo Nussenzweig. They are our neighbors here, only a few hundred kilometers away from Rio, where they have shown these 3-color entanglement experiments. So they have an optical parametric oscillator. You know, usually you have the approximation that the pump power is so strong that it's very weakly modified by the generation of photon pairs in the source. But if you have an efficient process or a cavity, an optical parametric oscillator, then you maybe need to take into account the fact that you annihilate one pump photon in order to create a signal annihilator photon. So you should witness correlations between all these fields, because this is a 3-wave mixing process. And once again, you have field correlators which allow you to measure these things and violate inequalities that certify quantum mechanics. So this gives us the clue that, you know, detecting single photons is really not the only way of detecting the quantum nature of light. So probably detecting single gravitons is not the only way of detecting the quantum nature of gravity. Of course, detecting single gravitons would be very nice and it would be very exciting. And once again, nonlinearity is source non-classicality. So a few years ago, I started to think about this, and I started with this question of what would the non-classical gravitational wave do if it hits a detector? So our detector will be just, you know, you can consider an interferometric gravitational wave detector like LIGO, but in order to simplify it, I considered only a cavity in my original paper. The basic physical idea is that as the gravitational wave impinges on the detector, the cavity changes its length, and this leads to a change in the mode of the cavity, which is proportional to the gravitational wave strain. So this gives you a dispersive optomechanical interaction. And when I thought about this, I was very happy because I know a bit about optomechanics, and so I can think in terms of optomechanics to try to calculate what a gravitational wave in a quantum state would do to a cavity. Okay. You can work this out from the Einstein-Hilbert action. You can do it very formally. It's been done. It's been pioneered by Yanbei Chen and Belinda Pang in Caltech back in 2018. And you really do derive this dispersive optomechanical interaction from starting from Maxwell's action and the Einstein-Hilbert action. So it works out very nicely. So okay, this is a Hamiltonian that we know how to exponentiate. It's very neat. It's been known for a long time in the optomechanics community. Okay, and in this model, the Hamiltonian basically gives you an evolution which can be split into two parts. One part is an optical squeezing or a Kerr nonlinearity part. Okay, it introduces squeezing to the optical mode of the cavity. And there's another part which is a phase shift, which gives you a phase in the optical mode, which now depends on the quadrature of the gravitational wave. And one thing that we need to observe is that this Kerr nonlinearity is always present. So we can call it a vacuum phase. Okay? This is something that will always be there, irrespective of the state of the gravitational wave that you are considering. And moreover, it is quadratic in the coupling constant. And by the way, the coupling constant is really, it resonates with what we were discussing previously with the neutron star Gedanken experiment. So it's essentially proportional to the energy to the frequency of the light in the cavity divided by Planck's energy times a factor here which depends on the gravitational wave vector. Okay, so if we look at this blue part here, the optical squeezing Kerr nonlinearity, we'll be looking at the effects of the quantum gravitational wave vacuum on the cavity. Okay, you can even generalize this. We've done some works where we talked about this with collaborators like Enrico, Antonia, and Francesco, who I think are here watching us, and Jennifer, where if you generalize this to a two-mode scenario, you will have entanglement because this Kerr nonlinearity now becomes a two-mode operator, and you can witness in principle entanglement between these cavities, okay, due to the quantum fluctuations of the gravitational wave mode. So if you work this out, unfortunately, the entanglement rate is prohibitively low. And why it's prohibitively low boils down to that factor, which is basically the energy of the photon in the cavity divided by the Planck energy square. Okay, so there's no hope to see this, but that's okay because this is just telling you that quantum fluctuations of the gravitational field are a Planck length scale phenomenon. Okay, so you need to be able to witness fluctuations on the order of the Planck length in order to see these effects. But okay, now we have a theory where we can compute the effect of various gravitational wave states. So like I said, we can pretend that gravitational waves can exist in different quantum states. And we've done that. So for coherent states, the answer is perhaps not surprisingly. You get that the optical state, if it is in a coherent state initially, it still remains a coherent state to a good approximation, but now it has a phase factor which oscillates with the gravitational wave frequency and it's proportional to the gravitational wave strain. You can consider squeezed coherent gravitational waves, which by the way are non-classical. Okay, they are Gaussian, but they are also non-classical if you look at them from the point of view of the Glauber-Sudarshan P representation. Okay, and these states also give you a signal at gravitational wave detectors. But now, depending on the squeezing of your gravitational waves, the signal can be exponentially enhanced or suppressed. Okay, and you can even calculate, depending on the squeezing, if it's a phase quadrature squeezing or an amplitude quadrature squeezing, you have the whole formulas for that. So it's nice. It will give you, if you measure these things, okay, it would give you evidence that gravitational waves can exist in these squeezed states. But this does not prove that you have a gravitational wave, a quantum gravitational wave, because you have classical signals which can mimic this. Okay, I'll talk a little bit more about this in the near future. Another thing that you can ask yourself is whether you can reconstruct the gravitational wave state. Okay, if you are, say, a super observer and you have a lot of technology and you can reconstruct perfectly the density matrix of the optical state, you can ask what kind of information you can hope to get from the gravitational wave. And what we can show, and this is work that we are doing in collaboration with Felipe Sobreiro and my student Luca Abraão and Pedro Paraguaçu, my postdoc, that the optical density matrix will depend on this correlation function, or on this characteristic function, which is a function of the gravitational wave initial state. And this function contains these correlators here, all the second order moment correlators of the gravitational wave field. So if you have a gravitational wave which spans two modes, for example, you could, in principle, collect enough correlators to violate a non-classicality witness and prove the quantum nature of gravity using these ideas. Unfortunately, all these correlators are multiplied by the tiny coupling constant, which scales as a ratio of the energy of the cavity to the Planck energy. So, I mean, this is just to say that the possibility of detecting this will depend really on how much energy the quantum gravitational wave will carry. And we have no theory for that. So we're a bit in the dark here. We don't know. Okay, so the idea is that this tiny coupling constant would maybe be compensated by a very large energy, very large amount of gravitons or energy in your quantized gravitational wave state.
As in, could you get an NH bar omega there? Or what the number of?
Yeah, you could definitely get an enhancement factor which depends on the mean number of gravitons on your state. Okay, in the case of squeezed states, you can get exponential enhancement in the squeezing parameter. So it's a possibility, but again, we have no theory for the generation of these states. So this is more of a phenomenological approach. Okay, you have to believe, you have to have faith that things like this exist in nature, and then maybe.
But to what extent can these? Maybe you said maybe you're going to go through this a bit later. But to what extent, if you have an enhancement with the number of gravitons, can
yeah, this is the work that we are. This is actually what we are doing now. So
right.
This is not out yet, but this is with these guys here, Felipe Sobreiro and Luca and Paraguaçu. We're looking at how large quantum gravitational wave states you would need in order to be able to detect these things with technologies that we have available now. Okay, so yeah, stay tuned. I don't have an answer at the moment, but
if you do use a large number, can some classical signal replicate those correlations? Or
so if you are able to measure all the correlators, you can set up a non-classicality witness, and then no classical signal will be able to reproduce them. You could do, for example, Duan's criteria, which works for second-order correlators. So this is why this is exciting. I mean, you could use this to actually prove that gravity is quantum.
I see.
But then again, we don't have a theory for the source, so we have to rely on the existence of the states, which is a very strong assumption. But okay, we'll see. Okay, so yeah, another thing that we looked at was gravitational wave decoherence. This is also in this paper here. I'm sorry, I should have written the names of the other people in this paper. As I said, Antonia, who's here, and Enrico, and Francesco Coradeschi, and Jennifer Rittenhouse. We looked into details if we could compute the gravitational wave decoherence for some examples. So, for example, if you have your cavity in this very non-classical state, you can, and you assume that you have a thermal gravitational wave background, you can compute that this state will decohere at a rate gamma, and this rate gamma is proportional to the temperature, and it has a factor which depends on the difference in the energy in the superposition. So this is, of course, it reproduces previous results from the literature, which is very nice. So we were very happy about it. So I'm going to use this hook on the gravitational wave decoherence to transition a bit into this topic of gravitational wave noise. So this is work that has been pursued by Maulik Parikh and Frank Wilczek and George Zahariadeh. recently, and also other people like Baylock who have studied stochastic gravity for many years. So the idea here is to use a slightly different model of a detector. So as we consider a cavity, these guys will consider just two freely floating test masses in space-time, okay? And they will look at the action for this detector in terms of the geodesic deviation vector of these masses. And when you write that, and you write the interaction of this geodesic deviation vector with the gravitational wave, okay, you can decompose the gravitational wave into Fourier modes, you know, the standard quantization procedure in almost flat space-time. You get this interaction here. It's a double derivative interaction, which is kind of weird at first sight. But if you look at it more carefully, you see that the action is actually quadratic in the gravitational wave modes. So this is amenable to path integrals. That means you can use the Feynman path integral method to compute these Gaussian integrals. Okay, and these guys have done this in order to analyze the semi-classical dynamics of this mass in the presence of quantized gravitational waves. So this would give you gravitational wave noise. Okay, so they use this Feynman-Vernon path integral method, which is nothing but a fancy partial trace. It looks very complicated, as it will in a moment, but if you think about it in detail, it's what they are doing here is really a sophisticated form of a partial trace. Okay, so you can compute a path integral expression for the detector's density matrix. Okay, in this case, is an element of the density matrix which gives you the transition between two states, A and B, of the detector. Okay, and this looks very complicated, but if you break it into pieces, it's actually not that terrible. So you have an initial condition part. Note that this is a double path integral because it's a density matrix. So you have a ket, a variable associated to the ket, and a variable associated to the bra. In the literature, people call this the forward and backward variables. Okay, and you have a probability density functional, which will give you this probability for the stochastic force, which comes out due to the quantum fluctuations of this jitter of gravitons. You have the free action of the motion of the particles, and you have the stochastic force. Additionally, you have a dissipation term, which turns out to be smaller, but it can also be taken into account if you want. So this is things that have been based on previous work by Feynman and Vernon and Caldera and Leggett. People in condensed matter and models of decoherence have looked at this into quite some detail. And lo and behold, you work all that out and you find that the geodesic deviation equation is given by a classical part and a modification, which is a stochastic force, which now causes your masses to jiggle a little bit around the classical trajectory. And you have a radiation reaction term, which is given by the dissipation that I showed before. So I would like to go for a little interlude on this, which is levitated optomechanics. So we in the process of learning these things from Maulik Padik's paper, we looked at whether we could transport this Feynman-Vernon path integral technology into quantum optomechanics. And it turns out we can. So this is this expression here is to be regarded essentially as a density matrix, or we call it the stochastic action of two particles in an optical tweezer. So you can think you have a double optical tweezer where you have two particles which are floating next to each other, and they couple via some interaction G, for example, a Coulomb interaction. Okay, and what you have is, again, you have the probability density over the noise. Okay, and you have this classical action, and you have a stochastic term due to the fact that one of these particles, say this X particle here, is in a quantum state. So what you are looking is, how does a classical system respond to a quantum state? It's a very interesting question. Okay, we've done that for the linear interaction, but this can be generalized for nonlinear interactions, especially because this path integral method is a very powerful method for doing perturbation theory. You can use it to compute various contributions in various orders in perturbation theory. So once again, lo and behold, you get a Langevin type equation if you take the semi-classical limit for one of these particles. Okay, and you have a force which is due to the quantum fluctuations of the other particle. And what is very nice now is that we can actually plug in numbers from the levitated optomechanics community, which are more or less realistic numbers that people are achieving in current experiments in the lab. And you see that this force is on the order of 10 to the minus 17 newtons if the particles are Coulomb interacting and if they are a few microns apart. So I like to think of this as the force of quantum mechanics. It's how tiny quantum fluctuations will do your semi-classical particle. So this is nice because it gives you hope to maybe measure these kind of effects in the lab. Okay, this has directly nothing to do with the quantization of the gravitational field, but it's just nice that you can think about analogous things in optomechanics. And one thing that was very important for me is that when we were doing this work, okay, I said, okay, let's plug in the numbers for a gravitational force. Let's look at gravitational induced noise, okay? So say you have one of the masses in a quantum superposition state of different locations and the other mass is semi-classical. And let's look at what's the order of magnitude of the stochastic force that this semi-classical particle will feel due to the interaction with the gravitational superposition. And you can cast this into this form here, so the force will depend basically on a rate. Okay, the numbers are very nice. It works out very nicely because it's h bar times a rate, which is energy divided by the 0-point fluctuations of the particle. So this is energy by length, which is force. It's a derivative of a force. And this rate, you can cast it exactly in the same way as the entanglement rate between the particles. So when I looked at this, okay, there's something funny here. I mean, obviously, this noise, which we attribute to the Langevin equation in the semi-classical limit, must have the same origin as actually quantum entanglement between these particles in a fully quantum description. So this clicked to me, okay, and it's kind of obvious after you see it, okay, if this noise will be a consequence of the quantum mechanical entanglement that these particles will develop. But since you are looking at the particle in the semi-classical limit, you will basically see it as just noise, okay? And this boils down to the fact that if you have a total state which is pure, the local density matrix is mixed if the local state is entangled. Okay, so if the total system is closed, the mixed substate implies entanglement. And these pictures are unified in this very nice work by Kano, Soda, and Tokuda, where they reproduced the results that Tariq Wilczek and Zahariad had obtained. And they've done it in a different way, slightly different. They used canonical formalism, which is also related to the input-output formalism of quantum optics, which is something which is, you know, more dear to my heart than the Feynman-Vernon path integrals, so I can understand it better. But moreover, in this formalism, you can treat the deviation separation vector as a quantum mechanical variable, and you can derive a sort of Heisenberg quantum equation for this separation vector. And what you find is that both the Langevin noise in the semi-classical limit and the decoherence of this deviation separation vector are due to the same object. So this really unifies this picture that the noise in the semi-classical limit is due to entanglement. Okay, so if you would detect gravitationally induced entanglement, you would also in a semi-classical limit look at, you would see tiny stochastic deviations of the motion of the particle, which is nice because maybe this will not again certify that you have entanglement because you cannot exclude that this noise is not coming from classical, but it's a nice evidence. Okay, and experimentally approaching this always as an experimentalist, maybe it's easier to have only one particle in a quantum mechanical state than to have two. Okay, but bear this in mind. This will be important at the final part of my talk. So if the total system is closed, then mixed state implies entanglement. That I'm going to use this clue later on. So as I said, all these things are nice, but as reminded to us by Daniel Carney and collaborators from Berkeley, detecting gravitational wave noise, single gravitons, squeezed states of gravity, that would be very nice evidence on the quantum nature of gravity, and I would be very excited to see that. But it would not exclude a classical model. In order to exclude classical model, I really think we should look into non-classicality witnesses. Okay, like this has been done in quantum optics by John Clauser back in the 70s, where he violated this non-classicality, this Schwarz inequality, essentially using his Bell type experiments. And I mean, this is what Bell inequalities are. Yeah, sure.
If I ask a question,
I see German already switched on. This is the sensitive part of the talk, I think.
Yeah. No. So but in some sense, even Clauser's experiments, they could be explained with a, say, in principle, some even more contrived model where you have superluminal signaling between the arms of the detectors.
Yeah. But like every Bell inequality, you can explain with non-local hidden variables.
Yeah,
right?
Yeah.
So
right.
I agree, man. I agree with you. Like if you measure tiny gravitational wave-induced noise on a classical particle, I think
it's good evidence.
I would personally be satisfied. I would go like, okay, this is spectacular. Okay,
and this is like this Clauser experiment is really like ruling out more loopholes, kind of.
Sorry, it's really what? I didn't
ruling out additional loopholes, I would say.
Yeah, exactly. Yeah, you can go paranoid. Okay, like I come from this community in quantum optics and quantum cryptography where people are really paranoid, and they better be paranoid because they want to do cryptography. So the beginning premise is that there is someone always trying to fool you into believing that you have a quantum system when in fact you have a highly controlled classical system. So you can go full paranoid, and I think we should to a certain extent. But that doesn't mean that it's not interesting to all these effects that we've proposed. Your graviton detection. The squeezed coherent gravitational wave, all those curves, how they modify the signals that LIGO would see, and so on. These are very nice, and I think they are very exciting. But we should bear in mind also that, to be really, a much stronger thing would be to violate an inequality like this Duan criteria here, for example. So this is really what Bell inequalities are about. So it's different levels of paranoia, I'd say. Okay, so we can discuss more about this later on, but I see my time is running out, and I really want to get to the end. So this, tells us that really to violate the experience from quantum optics will tell you that in order to violate a non-classicality witness, you strongly rely on two things. First, you need non-classical state generation, which we don't know yet if they exist for gravitational waves. Second, you need efficient detectors. Why do you need efficient detectors? Because these quantum states are often very sensitive to decoherence. Okay, in optics, at least, they are sensitive to photon loss. And if you have a non-efficient detector, then basically you can model that as a decohering environment previous to a perfect detection. So you need efficient detectors in order to violate non-classicality witnesses. So this will bring me to the final and second part of my talk, which is instead of just assuming that Schrödinger cat states of gravitational wave exist in nature, we ask ourselves, do they really exist? Okay. Can we say something about these states in more general terms? And can we ever hope to detect them efficiently? So there is one thing that I would like to emphasize based on that clue about the nonlinearities, that nonlinearity source non-classicality, is that gravity is different from electromagnetism in the sense that it can be highly nonlinear, highly self-interacting. Okay, and my current favorite example of this is from this paper by Mittman and collaborators, and also Cheung, where they showed with numerical simulations, that when two black holes collide, you have this ring down phase where the thing is settling down to a final black hole. And you can model that using first-order perturbation theory, the fundamental modes of oscillation of these black holes, but you can also look at higher-order modes. And they have shown that once these black holes collide, you get excitations of the higher-order modes, given an initial excitation of a lower-order mode. So these follow these quadratic laws here. So basically, the amplitude of the higher-order mode will grow quadratically with the amplitude of the fundamental mode. And this is numerical evidence of nonlinearity in general relativity. Of course, we have many other examples. People have looked at black hole oscillations, all sorts of gravitational waves colliding and so on. And there are many beautiful works on that. But this is just yet another example on the non-classical nature of gravity. Okay? And this reminds me very much of second harmonic generation, coming from an optics background. Okay? So of course, you cannot yet claim that that's what's going on there because we don't really know how to quantize gravity in a strongly curved situation, which is what they are looking at with these general relativity simulations. But it does feel a little bit like second harmonic generation. Okay? And in this nonlinear optical process, these interactions, these nonlinear interactions, they tamper with particle number distribution. So, for instance, if you would do parametric down conversion, you would end up with only amplitudes in the Fock basis of your state, which are even in the number of photons. And as shown by Hillary, this is non-classical. Okay. I've already given the example of the interference patterns, and also there is some nice work by the group of Mauro Paternostro that point out that in order to generate Wigner negativities, you can do that using generically non-classical interactions or non-harmonic interactions. This is just a nice Wigner function which I took from this Zurek's paper. Just to illustrate how complicated these things can be. So where you see blue here, the Wigner function is negative. So there's another aspect of nonlinear optics, which I think is not as very well regarded as the generation of non-classical states aspect, which I just mentioned, which is that nonlinearities can also act as detectors. So there's this paper from the late 60s by Shen, where he shows the quantum model of nonlinear optical processes. And it shows that the output of these nonlinear optical processes can depend strongly on the statistical properties of the input light field. So the statistics or the quantum statistics of the input will shape the signals that will come out. And he even he says, okay, measurement of the statistics of the output fields may yield information about the statistics of the input fields and the properties of the medium. So this is, to my knowledge, one of the first times that people have proposed using nonlinearities as quantum detectors. Okay, so you can understand this very quickly for some frequency generation as a, the nonlinear process always requires more than one particle in a quantized particle version of the picture. And if you have anti-bunched radiation, the chance that two particles will arrive at the nonlinear medium simultaneously is very much reduced when compared to bunched radiation. So bunched radiation will have more efficient conversion. And you can even do the math for the case of second harmonic generation, and you see that it's proportional to the G2 function. So it's sensitive to the correlation. Okay, so you could use, in principle, this to measure the G2 of your input field. It's been done experimentally more than once. There's one example here in this PRL from 2017. Notice again that the output number of particles is quadratic in the input number. So this quadratic behavior that I was telling you about. So, okay, let's, try to use the last minutes that I have available. I will try to argue with you that gravitational nonlinearities can indeed generate non-classical states. Okay. So to do that, I'm going to go into this limit of high-frequency gravitational waves. Okay, so this is very well known for many years, since the late 60s. So high-frequency gravitational waves, they are essentially gauge-invariant objects. So if you have perturbation of space-time, which has a very large frequency, meaning that it changes on a length scale lambda, which is much, much smaller than the radius of curvature of the background spacetime, you can compute the Riemann curvature tensor associated to this metric, and it will split into different parts. So there's one part which is given by the Riemann tensor of the background, gamma mu nu, and there is one part which is associated to these high frequency perturbations here. And this object is gauge invariance to order 1 over the radius of curvature of the background spacetime squared. So if you equate this to 0, it will give you a propagation law for these gravitational waves in the curved background. And it will basically tell you 3 things. First, it will tell you in the WKB approximation that you have plane waves, that the wave vector of your plane wave is a null vector. Next, it will tell you that the K vector is parallel transported along a geodesic that itself generates. And third, it will tell you that the polarization tensor of this wave is also parallel transported. Okay? So in other words, high frequency gravitational waves are gauge invariant objects which travel through a background low frequency spacetime essentially in the same way as electromagnetic radiation. So there's no qualitative difference between high frequency gravitational waves and photons. Okay. Moreover, you can look at this second contribution to the Riemann curvature tensor here. This defines a sort of stress energy tensor for the high frequency waves. And this stress energy tensor, you can use it to attribute the energy density associated to the high frequency ripples in the spacetime. And again, in the WKB approximation, if you do a little average over many wavelengths of your gravitational wave, this is called the Brill-Hardle average, okay? We don't need to go into the details. But you see that the stress energy tensor for these high frequency waves is essentially a null dust stress energy tensor. So these waves are really propagating just like electromagnetism or photons or massless radiation particles. So I'm going to argue now that if you place these high frequency gravitational waves in a background, which now consists of very weak low frequency gravitational waves, then these things will get entangled. And that's an argument for the generation of non-classical gravitational wave states through the interaction of gravitational waves. So first of all, let's consider the high frequency gravitational waves propagating in the low frequency background. Let's treat these high frequency waves as null particles, because that's essentially what they are in the geometric optics or WKB approximation. Okay. And now I will place my high frequency gravitational waves. Let's say I have 2 bundles of these massless particles, which represent gravitational waves traveling in space-time. But I will place one of them in a superposition of 2 different geodesic separation vectors. So this initially is a superposition state of Xi1 and Xi2 here. As shown by Kano, Soda, and Tokuda, this state will undergo decoherence. Okay? You can even generalize it to, Kano, Soda, and Tokuda considered massive particles, but in another paper by the group of Maulik Paric, this has been generalized for null particles. Which is referenced here in this JHEP from this year. You get essentially the same result of Kano, Soda, and Tokuda, which is that the superposition state of the different geodesic separation vectors of the bundle of high-frequency gravitational waves will decay, the coherence will decay, and the decoherence functional is essentially given by this expression here. So it's the ratio of the energy of the high-frequency gravitational waves to the Planck energy squared, and the mean separation vector that they undergo in this interference protocol. But the important part here is not the exact numbers. The important part is that, once again, if the total system is closed, then the mixed substate implies entanglement. Okay, so if in your theory, you are modeling your universe as just these low and high frequency gravitational waves here, then the decoherence associated to these high frequency ripples essentially signals to you that you are getting entanglement between these high frequency and low frequency gravitational wave fields. So this is the argument. I call it the first quantization argument because the high frequency gravitational waves are treated just as a bundle of massless particles. So you only do first quantization of the geodesic separation vector. That's why I called it first quantization argument. So this is not out yet, but I'm working out a paper which will explain these things in detail. And the conclusion is that low and high frequency gravitational waves can become entangled. There is also another interesting aspect of this, which is that due to the presence of this curved low frequency background, you can have entanglement between different high frequency gravitational wave modes. And I have reason to believe that the coupling can be quite strong. In fact, it can be proportional to the order of magnitude of the high frequency gravitational wave curvature tensor. And if we remember Bill Unruh's clue, if we want to see the quantum nature of gravity, we need gravitationally important objects. And okay, so if you have a chance of generating strong coupling between different gravitational wave modes, maybe you can use nonlinear gravitational wave processes to try to witness the quantum nature of gravity. Of course, there's a lot of work to be done. This is just a proof of principle kind of idea, no? But I think it's an exciting path, and it will probably, I will try to pursue this in the coming years, and we'll see. So with that, I'm done. I'd like to acknowledge my collaborators and students. We are the Quantum Adventures group at Pontifical Catholic University of Rio de Janeiro. So these are the guys who work with me. Most of them work in tabletop optomechanics experiments, with the exception of Luca and Pedro, who are theorists. Sometimes they work also on gravitational wave stuff. But yeah, so with that, I would like to thank you once again, German, and everyone for watching, and happy to answer any questions.
Great. Thank you very much for the really interesting talk. Do we have any questions? So I'll get going on. So coming back to the arguments on Klaus's experiment, because in some sense, depending on what you define as the smoking gun assumption that you're not willing to give up, any of these experiments could be a smoking gun signature of quantum gravity.
Yes. Yeah. No, I agree. No, I mean, even
in the sense of like with our graviton's proposal, I would say it's inconsistent with a classical energy conserving interaction.
Whereas I remember that argument, right?
Yeah.
Then you have to give up energy conservation or something like that.
Exactly.
And then things get weird. And
yes. Whereas with the Bell tests, it's local hidden variables.
Yeah, exactly. Yes. No, I definitely agree.
If you assign, So I suppose if you assign as much weight to the other assumption, then it would be equivalent in that.
Yes, probably. I don't know. I mean, I think the way things are going to go experimentally, if we are ever to measure any of these effects, then probably, we'll detect stuff, and there will be a model, and this model will be quantum, and it will agree with the experiments, and everybody will be happy. Well,
yeah.
I mean, good amount of people will be happy, and then there will be those who will say, no, you have to actually violate the non-classicality witness and so on. And
things like this would get around. But okay, if you want to do that with an interferometer, it seems you would need multiple. You'll need to build like a second LIGO, right?
Well, yes, but if you want to be super paranoid, I think you need two LIGOs, yes.
Yeah.
But you could have many different modes propagating the same interferometer, and then you could, but then people will say, okay, how do you show that these correlations that are imprinted in the optical modes are not due to some other effect since they are traveling together,
Right.
But yeah, if you want to be mega ultra paranoid,
you could use. So there's a set of orthogonal modes in the LIGO interferometer. You could just use different of those.
Exactly. Yeah. Yes. you could, send in a beam which is, full of different orthogonal modes, and that would sample, all of them would sample equally the gravitational wave because they will interact essentially in the same way. And then you just split them and you do tomography or whatever. You try to reconstruct the correlations in the gravitational wave by looking at the optical mode.
Right.
But yeah, I think that would be very hard. I think now,
honestly, have two resonant mass detectors. It'd be much.
Yes. Yeah, there are also people are looking. There's this experiments by Andrew Geraci where he has these levitated objects inside a cavity, and he's trying to look at high frequency gravitational waves. It's like a bar detector, as my understanding goes. It's a bit like a bar detector. So
a high frequency one, but
a high frequency one, exactly. Yeah. So that would be also very nice. I mean, it would open up possibilities, no? Because we know nothing about the signals that we could expect. So the more detectors we have, the better, I think.
Exactly. Get different types of detectors up.
Yes.
Yeah, including the resonant mass.
Yeah, including resonant bars and so on. Yeah. Do you know? Should I ask you? Do you know who's working on bars? There's people doing experiments on
yeah, there's one still in operation at that low frequency range in Italy.
Okay, nice.
It's the only one. The other main group, there's one in Australia, but they have now focused on high frequency gravitational wave detection. But now, since our proposal, they're interested in going back to the low frequency range.
Nice.
To bring back the resonant mass detectors for that type of experiment.
Nice. Very nice. Very nice. Yeah, maybe people will revive the bar community. I don't know.
Yeah, perhaps.
That would be cool.
Because then what do you think about the feasibility of the noise experiment? Say, looking at the squeeze states, because it seems like you need very high squeezing parameters to get any kind of
Yes, I think.
And so, do existing experiments with the light conformal place constraints on that? I imagine it would.
Right. Yeah, there is this paper by Mark Hertzberg, I think, I'm not sure if I got the name correctly, but there is one experiment which places a constraint. It's such a large constraint that I think you would need a very large amount of squeezing. Indeed, you need a very very macroscopic squeeze state, which may be hard to exist. I don't know, but maybe it does. Who knows? No, but I think if we go in this direction of looking at how gravitational waves interact non-linearly or non-linear gravitational processes, because the non-linearities can be very high depending on the curvature of the space-time, that would be a promising possibility. Even though there's much work to be done, we don't know yet. But there's definitely a possibility that, there will be some smoking gun of quantum gravitational effects. But then it's a tough problem because you need to know how to quantize gravity in highly curved spacetimes, which I'm not sure.
In order to get that type of signal, or
in order to even know what to expect, in order to even be able to calculate what because in quantizing gravity in highly curved spacetimes it's complicated because what are the observables? What are you going to use as your fundamental observables that are quantized? We know how to do that in weakly curved spacetimes. This high frequency limit that I was telling you about seems to be a good possibility because these high frequency waves are gauge invariant objects, so you can identify the degrees of freedom that you want to quantize very easily. So, and there the curvature can be very high because these high frequency ripples can be highly curved.
So maybe high frequency quantum gravitational waves exist.
Maybe, I don't know. Yes, maybe. Well, they do exist. No, I mean when the black holes are settling down, then that should be above 1 kilohertz, which is high frequency.
Yeah.
And it's also relative. I think it's all relative to the background. What's the curvature of the background with respect to the frequencies and so on. And there's
Yeah.
a lot of things to consider. But what I wanted to put forward is really this argument, because I think regarding the sources, we are so much in the dark here that we
Mm.
don't even know if these things can exist.
But I mean, at the
If,
very least, like with these gravitational wave detectors, be it resonant mass or LIGO, you can in principle through this experiment place constraints on the quantum state of the gravitational
yeah,
wave, as in certifying
absolutely.
coherence to within a certain precision. And
Absolutely, absolutely. But it would be nice to have some more predictions like,
right,
okay, if this thing happens, if this neutron star collides with this black hole, then
yeah. As in
it will
maybe for these
definitely
black
emit.
hole mergers, it's coherent, but for these other ones, it might not be. Or
Yeah, and then it will definitely create uh, a state which has this and that properties. It would be nice to be able to calculate these things. But it's, even the basic question of whether gravitational waves passing by each other, what the quantum state that comes out of this process is, seems to be a complicated question which people have no idea about. And so this is what I wanted to put forward with this first quantization argument, that yes, they can entangle because of self interactions of gravitational waves. So just sort of in order to convince ourselves that this is a possibility within the theory.
yeah.
So, and try to do it with more or less techniques and things that we have already in the community. So that's why I was talking a lot about the gravitational decoherence papers and so on.
But yeah, no, thanks for the very interesting talk.
That was very nice. I enjoyed it. Thank you for the invitation.
No worries.